Hey y'all, I'm Sunny Shell, and tonight Bree and I are thrilled to bring back Ethan Siegel to discuss his new book, Encyclopedia Cosmologica. So sit back, buckle up. Hey everyone.
Hey,
Ah,
Sunny. Looking
I
beautiful this evening.
Oh, you beat me to it because I was going to say that to you. We have been on hiatus for, gosh, 2 months now. And now we're back, and I'm so thrilled that our first guest after our little hiatus is Ethan. Thank you so much for coming on again, Ethan.
Oh my, Sunny Bree, it's my pleasure to be here. Thank you for having me back. And what a way to come back from hiatus. It's summer. We've got lots of good things happening. And for a lot of us, I don't know if you feel that way. For a lot of us, I feel like the last 3.5 years, they've been full of a lot of setbacks. And for a lot of us, some self-doubt. Like, am I ever gonna get back to where I was, feeling how I felt, doing the things I love to do? And so that you wanted me to be your first guest when you came back from this hiatus, and that you were saying, let's share this thing you've made. What I look at it, this is the first really big thing I've made since the pandemic and all of that. Like, I feel like, oh man, like this is what I want. I want this world where we have good people making good things, and we're doing our best to share them and promote them and get excited about there are things worth looking at again. There are things worth doing and seeing and sharing in.
Absolutely. And what's better than science? There's nothing better than science. Well, maybe sex, but other than that, there's better than science, right?
Science is pretty good. Science is pretty
Yeah.
good. I like to think about it as like you have a lot of different ways of knowing things, right? You have like historical truths and personal truths, but you also have scientific truths. And the beautiful thing about them is if we forgot all of them, if we forgot every person in history, whoever existed, whoever made a contribution to anything scientific, we could go out today and start from scratch. And if we did it right, we could reconstruct the same story. We could ask the right questions to the universe itself and get the same answer every time. And we would discover in time the same underlying laws that govern the universe and the same underlying truths about the universe we inhabit. And to me, that's a really remarkable thing. It means that millions of light years away, if there's another intelligent civilization out there, they've reconstructed the same thing. It means that if humanity somehow wipes ourselves out, but another species on Earth becomes intelligent, they'll be able to reconstruct the whole thing too. Like all of this stuff that we're figuring out, that we figured out till now and that we're still figuring out, like those laws of nature, those phenomena, they're always going to be the same. That's always happened. That's the true story. And we can actually know it just by looking at the universe we have in front of us.
Oh, what a great way to start our show. Thank you. That you're absolutely right. Before we get into some wonderful kind of cosmology and so forth, I want to talk about your new book because it's been going on. You know, you've been working on it for a while, and I know you have to be incredibly proud of it. And Wes, if you could put up the graphics. Look at that.
Oh,
That is
yeah.
so
What a
gorgeous. So I want to.
beautiful cover.
Yes. What is the inspiration for such a beautiful cover?
So what inspired that cover is there are all sorts of simulations that cosmologists conduct of the large scale structure of the universe. We call it the cosmic web. And what you see highlighted there is the backbone of the cosmic web, which is made of dark matter. And what follows the dark matter in our universe, the massive stuff that clumps, is us, is the normal matter, the stuff made of atoms, of protons, neutrons, and electrons. So where you see these filaments, galaxies form along those lines. Where the filaments are brighter, you get more and more groups of galaxies. Where the filaments intersect and you get those nexuses, those correspond to big galaxy clusters that form in the universe. And where you have those like Swiss cheese like holes in the universe, those correspond to what we call cosmic voids. We have a void near us called the Bootes void, Bootes. And that void has within it one Milky Way like galaxy, and then all around it for 100 million light years, no other galaxies that we know of. I call it the loneliest galaxy in the universe.
Sounds like it.
The inspiration for this cover was to say, let's take that large scale view of the universe that we can map out or that we can simulate, and let's let people get that visual impact, because this is a slip cover that it pulls out of.
Let's take one more look at that cover before
when you have the book in its cover, it's going to look like it does on the right. That's the part of the universe that we can see. That's the observable universe. But I want people to realize, to get that feeling when you pull the book out of the slipcover, I want you to get that feeling that there's more out there. There's more than what we can observe. There's more unobservable universe out there beyond what we can see. And I want people to get that sense of scale, to know that as big as our Milky Way is and as many galaxies as we know of, our universe goes on and on and on, not only as far as we can see, but almost certainly much farther than that. And we still don't know how vast it all is.
Did you pick violet because the ultraviolet light wave frequency that was supposed to be presenting, or?
Well, you know, some of these are meant to be what your eyes would see, and some of these are just, it looks cool like this. and sometimes you just have to go with, you know, when all choices are arbitrary, you could say, just this looks cool and I like it.
Yeah, I definitely would like to at some point talk about more details about the colorations they choose for different heavenly bodies and things like that with you, if you know anything about how they make those decisions as well.
Well, so those are, when we do those astronomically, like when we have photos from Hubble, you can actually take a red channel image with Hubble and a green channel image and a blue channel image and stack them together and see something like what your eyes would see. For an infrared space telescope like the JWST, for that, we have to do what's called assign colors. Human eyes can't see any infrared light. That's why when you touch that hot pot on the stove, the one that doesn't look hot, and you saw it wasn't glowing red, and you were like, oh, I was sure that wasn't, oh, it burned me. Damn it. Hot things don't look hot. That's right, you stupid brain. Right? That's the problem with infrared, is we can't see it. So what do? You have to say, well, we're going to say this shorter infrared wavelength range, we're going to assign this blue colored, and this more middling infrared range, we're going to assign a green color, and this we're going to assign a red color to. So we only have 3 types of cones in our eyes. We can only pick up on 3 fundamentally different colors. JWST has like 11 different filters to play with. So depending on how you group them together and how you colorize this, that's going to depend on what you see. But in general, we try and have things make sense, where you're saying, well, if things are, you know, shorter wavelength, higher energy, we know that's bluer and more violet invisible light. So we try to represent it like that. And if things are cooler and dimmer, that's generally redder wavelengths. So we try to colorize them on that same gradation that we do here. You can see down on the this way, on the lower right of your screen, you can see the Here Be Dragons. That follows a two accreting black holes, two merging supermassive black holes. And you can see that illustration is more violet towards the center because that's going to be the hottest part. And then as you move away towards the edges, it goes through the spectrum of colors from that blue down to more of a white, to a yellow, to an orange, to a red, because that's generally the higher energy is more violet, lower energy is redder. But if you just have normal matter and you heat it up, it's actually going to follow this curve in color space that goes from red to orange to yellow to white to a bluish white. And then it just peaks there. And it's like, nope, I don't get any bluer than that.
So beautiful. That's so cool. I love hearing about that. As we were looking at the cover of your book, there were other names listed. So can you tell us a little bit about the other author collaborators on this project?
Right. So if you know me, I'm Ethan Siegel. I'm a scientist, astrophysicist, and I won't shut up about science in the universe. And this is what I love. So I'm the primary author of the text of the book. And I also, on every page, we have calculations of what's in the universe at this moment. And I did those as well. The next two authors are Mark Garlick. Mark is actually, he has a PhD in astronomy, and he is a space artist based in the UK. And I love his illustrations. I love his style. For me, he's the best space artist in all of Europe working today. And wow. I think he's fantastic. So he's a great get for me. The third author on the book is also an artist. Mark and the other artist, John Lomberg, have both done all of the art in the page spread. So I've written the text and they've made the art. John, you may know from his fame of designing the Voyager Golden Record. You may also know him as the art director for Carl Sagan's original Cosmos series. And I was so excited to get to work with him on this. And I was so pleased to find out that he was actually excited to do this project with me too. So this worked out really well for that. And then our fourth author is Will Lidwell, and Will is actually, he's a graphic designer. He's an author. He wrote a very well received book called Universal Principles of Design. But what he did was, first off, this was his original idea. He was like, this is how I think we should tell this story. That we had Encyclopedia Galactica as an idea going back to, Isaac Asimov. And now we can do more than that. We can say, well, let's not just imagine what's out there in the galaxy. Look how big the universe is. Can we tell the whole cosmic story in an encyclopedic manner and make an Encyclopedia Cosmologica? And I was like, wow, what a great idea. I love telling the story of what is the universe, how did it get here, how did it become like it is today, and where's it headed in the future? That's pretty much all I think about. Boring, I know, right? No, it is. Like, I think about it all the time, and it takes a special kind of person to put up with me. But I dig it so much. And when I was approached with this project, I said, let's do it, Will. You design it, you do the layout, it's going to be so beautiful, like with the hardcover, with the insert jacket, with the art on every page. I love the first letter, and Will suggested having these sort of like epic titles to every chapter, like almost biblical in weight and importance. And I was like, what a smart way to do this. What a clever way to tell this story. And all throughout, like, I loved calculating little stats of it and having like, oh, this was the temperature of the universe. This is how many stars were in the universe. This is how many civilizations were alive in the universe at this time. It was so cool to get to make this together. And also, it wasn't like, oh, like this is Ethan's the author and this is what he thought. Like, no, there's a reason that all four of us are listed as authors, is because when we talked about what is this book going to be and what stories are we going to tell and how are we going to tell them, we all met together. This was something we all worked on. I might have written the words, but this is not like you're reading what Ethan thinks. Like, no, you're reading what the four of us put our heads and our knowledge together with and what we came up with.
Well, I think that's wonderful. One of the things that I thought was so cool when I was looking at your the sites that you have that talk about it was this beautiful. I'm going to put it up because this was not well. That's the Kickstarter. We need to have that. I clicked on the wrong one.
That's the best link. We've got all the info there.
It was this. The experience of the Encyclopedia Cosmologica will be like holding the cosmos in your hands, and to flip through its pages like traveling billions of years through space and time in mere seconds. I thought that was absolutely beautiful, and it made me want to get that book and experience that. So
that's a wonderful feeling, and honestly, that was Will who wrote that. I remember that. Good job, Will. Because this is really what we said is, look, we know the story of the universe. If we were to write it down, we could say the universe began as we know it 13.8 billion years ago with the hot Big Bang. And there's a before that too. And we tell the before the beginning story too. Because we've learned that the Big Bang is not the start of it all. The Big Bang's like the start of chapter 2. There's a whole chapter 1 before that, and we didn't want to skimp on that. We wanted to give it to you too. But the goal was, if we started at the Big Bang, we know today we are 13.8 billion years later. So let's say we're going to take the universe, we're going to start at time 0 at the Big Bang, and we're going to tell the story in 100 million year chunks. That first in the beginning page you're at over here, you're going to say that's 0 to 100 million years. And then you come forward to 100 to 200 million years. And then you come forward, and you do that with every turn of the page. You get a new art spread, new stats about the universe, and a new story that tells you something that's cosmically going on right then in the universe. And so you have to go through 92 separate spreads before you get to the creation of the sun and the solar system. And you have to go through additional before you get the first life on Earth. And then you have to go through several more before you get the first multicellular life on Earth, right? And so you have these stories that on one hand take us all the way out to the far recesses of the cosmos, where we talk about ultramassive black holes and civilizations that have lived and died long before our own came along. And yet here we are today, also looking at the history of our own planet and our own solar system, and, you know, trying to answer these big questions about, like, oh, geez, did you know that Saturn hasn't had its rings for most of the solar system's history, that it probably only got them like within the last 2 pages of this book, and you turn the page, if you turn the page 2 more pages in the future, it'd be gone. All these things that we think of are big and massive and really enduring. In the cosmic scheme of things, they're the blink of an eye. I think you have to get to the, if you were to scale this appropriately, the length of humanity, of all of humanity, would be smaller than the period at the end of the last sentence on the final page.
Oh, wow. I've heard something similar to that in a different context. I mean, in a different, it might have been Carl Sagan that said it. I don't remember, but someone had said that earlier about, like, if there was a big calendar and each day was so many years, I don't remember, we would be like a spot on one of the big.
Yeah, this was a Carl
days.
Sagan idea. He called it the cosmic calendar. And I remember doing the calculation and finding that if you said, I'm going to say all of cosmic history corresponds to 1 year, when does humanity arise? The answer is like, oh, the first human ancestors, like that we would say is our species, they come around at something like 11:59 and 54 seconds just before the end of New Year's Eve. Like
Yeah.
6 seconds before the New Year countdown, humanity exists. Whoop, and then it's New Year's.
Yep. That's right. I knew it sounded familiar. And who can ever forget Carl Sagan? Because I think growing up, he was one of the first, was the first person to ever get me interested in science and the cosmos and just thinking about something bigger than myself in a way that wasn't religious in nature. And that was wonderful.
I think he was that for a lot of people. And I love this idea that out there something wonderful is waiting to be known. And then you go and you start learning about what it is, and you say to yourself, oh my, like, this is so much bigger than any of the things we deal with here on Earth. Like, Earth is nothing in the cosmic scheme of things. Like, Earth is one of, trillions of planets in the Milky Way. And like many of those trillions of planets, it orbits one of the hundreds of billions of stars in our own galaxy. And also, there are like sextillions of stars distributed across trillions of galaxies in just the part of the universe that we can observe. And you want me to care that this person who looks like this is different from that person who looks like that? What are we doing, people?
I know it makes no sense. It makes no sense.
But also, I
Go
do
ahead.
love that we still have this cosmic story that unites us all. We can choose to look at the things that we all have in common, like 99.98% of our DNA, like this cosmic story of 13.8 billion years that culminates in 8 billion of us being alive on this planet at the same time. Like there are some pretty amazing things about existence. And I think trying to get a feel for that cosmic perspective is something that we miss when we don't have it. But when we expose ourselves to it, our lives become richer because of it.
I agree. That's beautiful. Before
Can
we
I
go
ask
on
a
with
question? Oh,
Yes,
great.
You
go
can
ahead.
ask me anything.
All right.
Your
So,
hair matches my shirt.
when our sun swallows up this planet, this little tiny dot of a planet, will our remains be energized and sent out to the galaxies?
Well, I don't like to say when. I still like to say if. I agree that that's more probable than not. But there are estimates of what's going to happen over the next 7 billion years as the sun becomes a red giant. And we know two things are going to happen. One is it's going to get hotter. And after about 2 billion years, it's going to get hot enough that it's going to boil Earth's oceans away. So if you want your remains to see the red giant phase of the sun, don't bury it at sea. No, oceans are going to boil. That's bad news. Deep underground, maybe somewhere in like the Mariana Trench or the Tonga Trench or one of those other subduction zones that'll take you deep into the earth to be safe in case something bad happens to the surface. But then, as the sun loses mass, it's going to make Earth spiral away from the sun. Now, the sun's going to expand also. So how big will the sun get? The answer is about 115% of where Earth's orbit gets. So it should swallow Mercury and Venus for sure, and probably the Earth. But the Earth's also going to spiral away a bit. By how much? The answer seems to be about 10%. So we don't think Earth's going to get out, but it's going to be close. It's going to be close, and I don't want to sell us short. Maybe we'll survive. Maybe we'll survive. In something like 1% of the simulations, before the sun becomes a red giant, one of the 4 inner planets will actually get ejected. So I don't want to say it's a certainty, but if that happens, if the sun swells to a red giant, as soon as it engulfs a planet, normally we go around the sun and there's nothing to run into. But if the sun expands and we start running into the outer layers of the sun, then instead of going around in a circle, we're going to make a spiral and we will get swallowed by the sun. And yeah, if that happens, the molecules that we have in the earth are going to decompose and just become part of an ionized plasma in the interior of a sun. So if you bury yourself deep enough and you make it to that and the sun swallows the earth, that is what will happen to you and all of the atoms here on earth.
That's so cool. And then it'll go
Long-term goals,
supernova.
Bree.
And
I like it.
that's awesome.
Thank you for that question.
Yeah.
So before we go on, well, first of all, I am sorry, Bree. I have just been asking questions like crazy. Didn't even give you a chance to say anything. I'm terrible.
No, it's okay. That was my question. That's what I was thinking of the whole time he was talking about it. I'm like, the way that stars, because on a cosmic scale, right? Stars come to life and die all around. Our sun's not special, but us, we're kind of special on this little dot here, right? We're kind of special.
There is
So
something special about us, isn't there?
Yeah.
Most planets don't have stuff like us, but I'm
Mhm.
curious about the ones that do. I'm
Yeah,
really
for
curious
sure.
about the ones that do.
I wonder though if our planet feels like it's special that they have us on the way that we're treating the Earth. But anyway, I digress. So here's a question from the audience from Logan Fisher. He says,
Oh.
I just saw the littlest girl goes inside an atom. I love the idea of communicating science to kids. What do you feel is the most misunderstood topic that can use more education? Great question, Logan.
Wow. That is such a good question. I will tell you that The Littlest Girl Goes Inside an Atom is a book that I co-wrote with a particle physicist because she came to me after meeting me and said, Ethan, I have a son, I just had a daughter, and I wanted to get some science books for my kids. And I found that they're all about dinosaurs or planets. Everything is about dinosaurs or planets for kids. There's nothing about, for example, I'm a particle physicist, the scales of the very, very small. And I said, you're right. Let's write one. So we came up with this story of what do children do? They ask questions like, and then what? And what's inside that? And what happens if you go smaller than that? Like they always want to know, and then what, until you can't answer anymore. And for the parent of a curious child, this is exhausting, but it's also extremely rewarding because you have a child who's curious to know, what are the limits of our knowledge? Tell me what we know until you can't tell me anymore. And I feel like that spirit of asking those questions, of continuing to stay curious about it, that's the most important thing to foster in a child. So I would say, regardless of facts or specific topics that I would say a kid should know this or not know this, I want them to know that the way you understand things is you keep interrogating it. You keep asking it questions until it gives up its answers. Not like a lawyer in a courtroom, but like a scientist in a laboratory. That's what you do. That's how you investigate reality. And that I feel like is something that not only children but grown-ups need to know too, because so many of us get taken in by, we hear this wild story and we're like, that story's wild. Did you know that's true? That's wild. And then we go off and we repeat it 100 times. And then finally someone who knows comes along and tells us, no, let me tell you what is true. Let me tell you what we know and how we came to know it, and how if you wanted to know it, you could find it out by asking these same questions yourself. That's something that I feel like is really missing. So when we wrote The Littlest Girl Goes Inside an Atom, we thought it was important that the girl is doing the adventuring, and the girl is asking the questions, and the girl is finding out answers for herself, and she's going inside this water until you can see the molecules, and she's going deeper into the molecules and shrinking down more to see what's inside them, and she's going down into an individual atom to see the electrons in the nucleus, and then she's going inside the atomic nucleus and seeing what's going on in there, all the time remembering that this is a kid's story about exploration and adventure and being hungry for pizza and all the important things that kids are. So, you know, thank you for your interest. And I hope that any of you who get this book, which, by the way, you can get bundled with the Encyclopaedia Cosmologica if you pledge our Kickstarter.
Yay!
Like, I think that this is really an important thing. Now, there is a book out there for the very small, for scales of the very small. It's called The Littlest Girl Goes Inside an Atom. And I had a lot of fun writing it, and I hope you have a lot of fun reading it.
Fantastic. Absolutely fantastic.
I hope I answered your question. That was a good one, Lucas. Thank you.
He said, great answer. Thank you. So, or wonderful answer. Excuse me. Wonderful answer. Thank you. So I think that you did. What a great thing. If we can keep our kids interested in, you know, learning
and don't discourage them from asking questions. You know, I know a lot of people, it's tiring. It really is tiring, but that sense of curiosity, make sure you keep that alive, because an incurious adult, boy, I don't know what to do with those.
Yeah, absolutely. I used to, with my kids, I used to say, there was a lot of things I didn't know. They would ask all those questions. It was very quick when I would be like past the point of knowledge. And so I would say, well, why don't we go figure that out? You know, and, you know, when my first was really little was right when the beginning of people having computers. I know that tells how old I am, but so, you know, we actually still had things like encyclopedias, like a whole big library of them, which I loved. I kind of wish we had them still, but even so, you know, once I had more kids, we could just go to the internet and look things up together. And you know, that's a time for parents to bond with their kids, as well as keeping them interested. And they understand, hey, it's okay for us parents not to know everything. It's okay. That doesn't make us a bad thing.
Well, if you knew everything, then what would you have left to learn?
Exactly. That's exactly right. So back to your book, I had some more questions for you. One of them, sure, we've kind of already answered a little bit, but just in case there's something that you haven't said already, what inspired you to write this book?
Oh boy. A lot of authors, a lot of writers, or storytellers of any type talk about having a story inside of them. And for me, I have that story inside of me is what I've learned by studying the universe is like, no, like, where did it come from? How did it get to be the way it is today? Where is it headed like, what is it and what's going to happen to it in the future? This is something that is not a question of speculation in a lot of ways. It's not a question of like, I think, and I, you know, no, there's no pretend, no make believe, no appeals to things we aren't pretty sure of. This is the best information we have and best rules we've been able to figure out indicate this, that it was like this, it did this, it got to be this way, and here's what it is now, and here's what it's projected to do in the future. That's amazing to me that science can do that. We have had for thousands of years people asking these big questions with no clear answers, right? We had the whole fields of philosophy and theology, and honestly, most of poetry too, is people talking about these great unknowns and making up stories to fill in what they don't know. The stories we're making up to fill in what we don't know are so small at this point. They are what Carl Sagan would have called they are the gaps in our they are these ever receding gaps in our knowledge that are being filled in by what we're actually learning and making sense of. And that's remarkable that we filled this in. So what inspired me to do this was, look, yeah, Will came along and he gave me the right opportunity at the right time. But I'm going to tell this story again in as many different ways to try and reach as big an audience as possible, because this is the sort of thing that it shouldn't just be me who knows it. It shouldn't just be me and a few thousand other people with PhDs in theoretical astrophysics. This is the story of the universe, and it's your universe too, just as much as it is mine. So if I know some stories about it, I bet you'd be interested in that story too, even if you didn't know the same types of mathematical details that I knew about it. You still want the story. So let me give you that. Let me tell you the story, and you don't have to worry about the math. I did that hard part, so you don't have to.
Excellent. Excellent. When you were describing kind of the way that you were writing this book, that you and your collaborators were kind of working on it, you said that there were 3 overarching principles that you
I
adhered
did.
to.
I have said this. I will tell you what they were. I assume you were going to ask, what are these 3 overarching principles that you held to when you wrote the book?
Absolutely.
All right. So the first thing I wanted to say is that the universe itself, and this is an assumption, but that the universe itself unfolds naturally according to the physical laws of nature and without requiring any sort of supernatural intervention. So we're just assuming that it's the laws of nature that are at play that have led to the universe becoming the way it is. The second assumption is that those laws that we've inferred, that we've measured, what does the universe do and what is it like, we assume that those laws apply everywhere and at all times and are not special. They're not special to humans. They're not special to planet Earth. They're not special to our solar system or our Milky Way or any way of sort of saying our specific here and now in the universe. The universe unfolds naturally first, and that the laws that it obeys them everywhere and always. And then that third principle is that, look, when we tell stories, we're gonna run into stuff that science isn't certain of yet. We have a leading theory, or we have some thoughts, but no one theory is the consensus yet. And when we have that, what are we going to do? So we say wherever we lack the direct evidence to support one scientific scenario over another, we're going to offer what we call informed speculation, which means we're going to say, like, this is a likely way it could have happened. But we're going to demand that any speculation we do be reined in. It has to be fully consistent with all of the available knowledge and not in conflict with any observed truth or underlying theory about reality. So you will get stories of, when did the first life in the universe arise? Obviously, we haven't figured that out, but we don't want to omit that part of the story because we don't know all the details. We're gonna give you informed speculation on that, and we're gonna provide you with some considerable details that pretty much take us up to the frontier of knowledge. So we're not gonna not tell part of the story because we haven't got the details worked out, but we're also not gonna say something like, and then a golden man with a lightning bolt on his hand rode in and threw his lightning bolt in the pond scum down there, and life arose. Like, we're not doing that either. Fully consistent with the laws of nature as we know, with no supernatural intervention. Is that what definitely happened? Can't say for sure, but that's the approach we take in this book.
Very good. I like that. Someone in the notes said, let me see if I can find it. Oh, where was it? Here it is. Takes notes. The universe itself unfolds naturally. And naturally, I thought that was a good summation. I love that.
Yeah. It's not like the James Webb Space Telescope. That one unfolded because we engineered it to unfold.
I saw a fun question in the side chat from our buddy Theo out there, theoretically, about what's your opinion on these UAP hearings and the biologics claims that this guy was making as someone who studies the stars.
Oh, Theo. You know, on the one hand, it makes me kind of sad because we have real scientists investigating the question of life on other worlds and intelligent life out there in the universe. And we have people who've devoted their lives to searching for these signals. And then on the other hand, we've always had groups of people with, I'll say, limited expertise and limited experience at the frontiers of science, seeing something that they don't know what it is, which happens to all of us, and then saying, and therefore aliens, and therefore non-human biologics, and therefore, no, that's not how we do things. You'll hear it many, many times, I'm sure, from scientists and non-scientists alike. We found life beyond Earth. You will hear this announcement over and over again. You may have even heard it when people talked about finding evidence for phosphine on Venus, right? Which is dubious, not definitely no, but not generally accepted either. Now you look at this and you say, okay, it's easy to make a splashy claim, right? We found this thing we've been looking for a really long time. People have been going bonkers about this on the internet recently with room temperature superconductor. The answer is almost always, look, if this is real, if what you say is real, you have to present the extraordinary evidence that would back up this claim, where even a reasonably skeptical observer would be convinced by it. How do I know this is non-human biologics? Oh, I have a specimen here. Sequence its nucleic acids and see that in its genome it has a completely different structure from DNA and RNA. It's a new type of nucleic acid based on a peptide. Look at this. Oh, well, now I'm convinced because I wouldn't know that such a thing could exist. And you've shown me the example. They don't have that example. People who are claiming aliens, like, what do they look at a video of a naval footage of someone's own plane's reflection in their own radar instruments and go, oh, that's an alien. People look at, oh, like he said this thing, it moved off faster than I knew how it could go. It's an alien. Like, oh, I found these metal spheres at the bottom of the ocean. Alien. No, this is not how we do things. Which is why I find it sad, because this is the same breakdown that no one is telling the small child who's curious what is true. What do we actually know? How do we know it? I wish my role in this world got to be more about sharing the beautiful things I'm excited with than playing this never-ending game of whack-a-mole of claims that, people can have their 15 minutes of shame saying whatever they want. Yeah, that was not a Freudian slip. I said that on purpose. Because they could say whatever they want and they'll get the attention. But the thing is, don't come to me with a big, world-changing claim that's only half-baked. The number of half-baked claims that turn out to be true because you see, we fully baked them later is zero. No, bake your claim fully or don't show up because you have a big nothing burger. All you're doing is making more noise, and we don't need more noise. We need more truth.
Absolutely. Well said. Thank you so much.
Wonderful.
Yeah, that was great. So that kind of I guess it kind of segues into my next question, because
You're
I
always
am.
full of questions, Sonny. Mhm.
So did you have to revise any parts of the book because of the results of the JWST?
You know, I will tell you, especially about the earliest times in the universe, we had to make some speculations. And we started this book near the end of 2021, back before JWST launched.
Yeah. So
So we didn't have the JWST data that we had today when I started writing it. Some things did have to change. I overestimated. I estimated too big a time for the amount of time it would take the universe to form galaxy clusters. I had to revise that estimate back, those nexuses of the cosmic web, the rich collections of galaxies, where instead of having a local group where it's us and Andromeda and then like 100 or so other like little rinky dinks, no, we're talking of a cluster with like thousands of Milky Way sized galaxies, like where we're looking at things that are quadrillions of solar masses, not like 1 trillion. Like we're like real biggies over there. They formed earlier than we thought, and the JWST has shown us that you get protoclusters earlier than we knew with Hubble. You get fully formed clusters earlier than we saw with Hubble. And that was one that was surprising to me. I knew it was going to find evolved galaxies earlier than Hubble had found. I knew that we had to form stars and the seeds of supermassive black holes before we had detected them. I was within a reasonable guess. Like I was in the same 100 million years of my guess for those, but for galaxy clusters, no, things got bigger faster than I realized they would, and that was a big thing that I had to revise.
So, was it because I've heard that um, from other scientists, and I'm wondering, was it the math that was off?
So there were claims that people made early on that said, look, JWST is seeing galaxies too big to exist too early on. And this was based on these cosmological simulations that were done, where we basically say, well, we think we know what the universe was like when it was born, and it had this type of mass fluctuation in it, and we can simulate it. How do we simulate the universe? Well, you make a big box, and you put as many particles as your computer can handle in it, and you say each particle is this big, and you model the expansion of the universe, and you model gravity, and you look at how things clump and cluster together. It turned out that when you run those simulations, you generally came out with a universe that formed the majority of the structure it forms, galaxies, clusters of galaxies, later on than what JWST saw. And there was a big question of why. Is it because, number one, we've got our theory of the universe wrong, and we're simulating it and we're just not getting what we're seeing? Number two, is JWST performing the way we expect? It's a new instrument. Is it calibrated properly? Or number three, is there a problem with the simulations? If we made these simulations, if we had more computing power and we could put more particles in and we could see things in finer details on smaller scales, would that change the story? It turns out number one is not true. The universe looks pretty much like what we thought it did. You don't need to make it older. You don't need to change the ingredients. You don't need to make some sort of cockamamie scenario about like, we've got primordial black holes that it was born with, and these black holes suck everything in. Like, no, you don't need to do that. Number two was partially true. We had expectations for how JWST was going to perform, and it wound up beating them. JWST is a better telescope than we designed it to be. Part of the reason is that It is the cleanest telescope we've ever built. All those photos you saw of it, of the clean room at NASA with the people in the white suits, right? All of that, this is a continually improving thing. JWST had less dust on it and a smoother surface and fewer minor imperfections, fewer pieces of earth dust clinging to it than any telescope ever. Part of why we're seeing things crisper and cleaner and brighter than they were is JWST is actually performing better than we thought. So a lot of these, oh, how did this get so bright so early? It's not actually that bright. You just are looking at it with better eyes than you knew you had. It's sort of like if you opened your eyes at the bottom of the ocean and you were like, why am I seeing all this stuff? And then you look in a mirror and you see your human eyes have been replaced with soccer ball skies, squid eyes. And you're like, oh, that's why I'm seeing so well, because I didn't know I had eyes this good. But part of the reason is also, and it was a really underappreciated paper, I think, that showed this, is we were using these coarse medium resolution simulations. But when you change that attitude and you start to say, well, let me look at the highest resolution simulations, and specifically let me focus in on those high resolution regions that happen to have the greatest overdensities, those like 0.01% regions of the universe that are like not just like 0.03% denser than average, but like 0.12% denser than the average. It turns out that completely changes the story. That's where the majority of the most massive early galaxies come from. And the thing that baffles me about it is we had these simulations as early as 2013 and 2015. It was a suite of simulations called the Renaissance simulations that actually said, hey, we're going to use this technique called adaptive mesh refinement, and we're going to take a look at the densest, smallest regions and monitor how they evolve very quickly. And it turns out that you can actually get tens of thousands of solar masses, enough to make the first stars, enough to make the black holes, when the universe is like 140 million years old. So all these people who were like, oh, 300 million years after the Big Bang, you shouldn't have a galaxy there. We're like, no, yes, you should. Look at that simulation. You know, the one from 2013 and 2015 that you didn't bother to look at. That's the one that predicted them. We got it right. And if you use that simulation, you will see, oh yeah, all of this large scale structure appears to match up very well. So it was none of column A, a little of column B, and mostly column C, where no, you don't break the universe. There's nothing wrong with it too early, but the telescope actually is really overperforming, and that's super awesome. And also, yeah, you have to use the right simulation. You have to get to high enough resolution. Don't cheat us, man. Don't cheat us and be like, oh, I put my blurry glasses on and I was like, how'd you get a sharp thing? Well, put your sharp glasses on.
Oh,
I love that answer. Okay, so moving on. I'm going to go away from your book a little bit because I know that especially Kat, behind the scenes, she has been really wanting to know what the most common misconceptions about the universe are.
Oh boy. So I can really only go by the ones that I hear, right? Because I don't really know all the ones that I don't hear about. But I know a lot of people, the most common misconception I would say is even if they know about the Big Bang, they have misconceptions about it. They think it was an explosion. They think that it was the very beginning of everything, including the birth of space and time. And they think that the Big Bang is also very much in doubt. That the Big Bang is just our leading theory now, but maybe someday we won't believe the Big Bang at all. And I don't think any of those things are true. You know, the Big Bang is an idea that can trace its origins back to the 1920s, or in some cases, if you argue it, I don't believe those people. Some people say De Sitter in 1917. I don't think so. But the 1920s, that's 100 years ago.
Mm-hmm.
People were resistant to these ideas. People were skeptical. People threw every alternative they could at them. The thing is, there are 4 cornerstones of observations now that indicate that our universe, the way it is today, wasn't always like this, that it only became the way it is today because it has expanded and gravitated over billions of years of cosmic time, and that in the past, the universe was smaller and denser and hotter and more uniform. And as you extrapolate back and back and back, you can come to this early time where things were very hot and very dense and very uniform. And all of what we have today arose from that early state. That's all the Big Bang is. That's why sometimes instead of the Big Bang, I call it the hot Big Bang, so that people don't get wedded to that old, outdated idea of, oh, singularity, birth of space and time. Yeah, I'm 1927. Like, no, come on, come further than that too. But the Big Bang has 4 cornerstones. One is this large-scale cosmic web that we've illustrated. Theory predicts it, simulations predict it, and we observe it. We observe how the universe grows up. This is one of the huge lessons that Hubble taught us and that the James Webb Space Telescope is teaching us. Number 2 is the fact that, oh, well, if you go back and back and back, you can see the universe as it was in the past. And we can see it was hotter in the past. It was denser in the past. Galaxies were smaller and less evolved in the past, and they've evolved and are more massive now, right? All of these things of evolution we see indicates the universe has expanded and is still expanding. We have a wide variety of measurements that support that. We also say, look, I can extrapolate, okay, the universe is like this now, but if I come back and back and back, it was smaller. And because light has a specific wavelength, and the wavelength of that light determines its energy, if the universe was smaller in the past and smaller in the past, then that wavelength of light was shorter in the past, which means higher energy, which means hotter. So at some point you can imagine, whoa, it was too hot to form neutral atoms. All you had was an ionized plasma. Well, what happens when plasmas become neutral? All the light that was bouncing off the ionized electrons now free streams throughout the universe, just streams unimpeded. We see that leftover light. We detected it back in the 1960s, and it's still there in all directions. That's what we call the cosmic microwave background. I like the older name for it when we called it the primeval fireball. Boom.
I love that.
Ooh, that's an awesome name.
I know. Look at us. We used to name things like electron after their amber color, and now we name things like gluon because it's like sticky and stuff.
Yeah.
Like we got a lot less poetic as time went on. But primeval fireball, we see that. And the 4th cornerstone is, you can imagine going even hotter than that, to when we couldn't even make protons and neutrons bind together. Well, we see the light elements from when you finally could bind them together. Hydrogen, its isotope deuterium, helium-3, helium-4, isotopes of lithium. We can detect those from pristine samples of gas that have never formed stars before. And we see, yeah, they had none of the heavy elements that you only make inside stars. So all of those 4 together, the large-scale structure of the universe, the expansion of the universe, oh, that's a very sweet compliment. I promise you, I will not be the next Carl Sagan. I will be the first Ethan Siegel. And history will have to tell what that looks like. But I don't want to be anyone else. I only want to be myself. And I wish that for all of you out there. Don't try to be the next version of someone else. Be the best version of yourself.
Absolutely.
The third
Yep.
one is the cosmic microwave background. The fourth is the abundance of the light elements. No other theory explains all four of those. If you can come up with an alternative that explains those four, you've got a real alternative to the Big Bang. People claim they do all the time, and when we look at them in detail, we say, no, your spectrum for your CMB is not black body. Get out of here. Nope, you make too much carbon. We don't have carbon. Get out of here. No, your universe doesn't follow the expansion rate we've observed. Get out of here, right? There's always a reason that if you look at it in detail, it falls apart. So that's what you have to do. You want to make an alternative theory, you better not let the current theory beat you. You got to go and beat it on its own turf.
Kat also wanted me to ask you if you can explain what they actually mean by a singularity.
Okay. A singularity in physics and mathematics is a point where your theories break down and don't make sense anymore. It's basically like saying 1 divided by 0, right? That's not just infinity, it's undefined. A singularity is like that. So you would say, look, if my universe was big, right? Big. And then in the past, it was smaller and smaller and smaller and smaller. How small can I go? How small can I go? Well, if your universe is filled with matter or radiation, the answer is, oh, well, in a finite amount of time, you just go down to 0 size. And 0 size is a problem because you have a finite amount of stuff in 0 size. What does that mean? That means I have infinite densities. It means I have infinite temperatures. Well, this is bad because at energies above what we call the Planck energy, all of physics breaks down because any quantum perturbation you make in space is going to make a black hole, which is a singularity at its center. That's clearly not what the universe does. This doesn't make sense. So some people call this the quantum gravity limit. But in general relativity, it comes out to a singularity where you say, okay, we know this doesn't make sense. So something had to happen here, but it isn't described by the equations we know. The thing is, we know the Big Bang only takes you back so far that if you say, hey, was the universe always hot and dense? The answer is no. There's a limit. There's a limit to how hot and dense it could have gotten. And before that, the universe wasn't full of matter or radiation. Instead, it was full of what we call energy inherent to space itself, like the energy of empty space, like today's dark energy, except really, really high, a really big value of it. What does that mean? It means if you go back and back and back and back, then once you get that transition from where the universe is matter and radiation on one side and energy inherent to empty space on the other side, now when you go back, it doesn't go to 0 in a finite time. Instead, it goes back, 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 and never reaches 0. It only approaches it, but never reaches it. That won't end in a singularity. That is a type of space-time that people who study it don't like. They say, well, this is a past time-like incomplete space-time. What does that mean? It's space-time that doesn't begin with a singularity. What does that mean? It means what we talk about as before the Big Bang, as this state of what we call cosmic inflation, either it truly went on for an eternity and there was no singularity and there was no beginning, or there was a beginning and cosmic inflation isn't the start of chapter 1 either, but rather there's a chapter before that, which makes cosmic inflation chapter 2 and the Big Bang chapter 3. And we don't know what came before it. This is one of the benefits and curses of cosmic inflation, is it tells us what came before the Big Bang, but it doesn't tell us what came before that tiny final fraction of a second of cosmic inflation. So this is the reason why a lot of people don't like cosmic inflation. But to me, that's a feature. We learn something more. Now we have new questions. That's pretty much what's always going to happen. When you learn something new, you're going to learn it to the limits that you know it, and it's going to bring up new questions and get to work.
That's right. I love that. Oh my gosh, my brain is exploding now with all these questions. But I'm going to stick with the ones I already had. Otherwise, we'll be here forever. But I want to ask you one thing. I know that I usually only keep you on for 1 hour. We're already past that. And I want to make sure that I'm being respectful of your time. Can we ask a few more questions?
I knew we were going to go a little long, so I planned for 90 minutes.
Okay,
so
great.
You've got me for another 17.
Okay. So I'm going to try. I'm going to have to skip some of the questions that I had, but you touched on a few that I already had going. So I'm going to start with, what is the difference between dark matter and dark energy?
Thank you for that great question. Bre, I know that was your question. So this is really good because we have all of this normal matter, all the stuff made out of the particles in the standard model that we know of, right? The quarks and gluons that make up protons and neutrons, electrons, their heavier cousins muons, their antimatter counterparts, the positron, we have neutrinos, we have all of these particles. That makes up about 5% of the universe. Oh, and the photon, don't forget good old light. Thank you, light. 5% of the universe. What's the other 95%? Well, we mostly know about it from how the universe both expands and clumps together. The universe clumps together like normal matter is only about 1/6 of the massive stuff that's there. The rest of the matter clumps together, not like normal matter. If I take normal matter and I smash them together, they're gonna splat. We literally call this process pancaking in astronomy. Matter, splat, pancake. That's what we call it. Why? Because it interacts with itself. Matter and matter interact. You smash them together, they will heat up. They will radiate energy away. They will bind together and make complex structures. Things like galaxies and stars and planets and all the goodies we get, right? Dark matter can't do that. Dark matter is something that if I take a dark matter particle and a dark matter particle and I go to collide them, they will pass right through each other. If I take a dark matter particle and a normal matter particle and I go to collide them, they will pass right through each other. Dark matter doesn't smack into itself. It doesn't collide. It doesn't lose energy. It doesn't heat up. It doesn't radiate. It doesn't annihilate. All it does is gravitate. And the rest of everything else, all the other forces of the standard model, it's indistinguishable from invisible. It does not experience electromagnetism. It does not experience any of the nuclear forces. All it does is gravitate. That's dark matter. Dark matter on large cosmic scales clumps and clusters together into small and large halos, these big spheroidal shapes. And at the centers of these dark matter halos, you get stellar structures, things with stars and planets and galaxies and all that stuff in there. Dark matter halos are big and massive and drive the formation of structure in the universe. They are, in many ways, the backbone of this cosmic web. Dark energy is different. Dark energy is everywhere the same. It's like, again, some type of energy inherent to space itself, saying, well, you can do what you want. You can gravitate, you can make clumps, you can make galaxies, stars, whatever. Make what you want where you want. I'm the same everywhere. I'm just going to work with my positive energy to keep expanding the universe and making more empty space between these bound structures. So that's what dark energy does. Dark matter is like your strong man doing the Hercules hold, where he's got like, you know, the pillar that's going to fall over one way and the pillar that's going to fall over the other. He's trying to hold it together. And dark energy is like pushing it apart, and dark matter is trying to hold it together. And it turns out that dark matter can win on the small scales, which is why we have a solar system, and why we have a galaxy, and why we have a local group of galaxy, and why over there we see clusters of galaxies. Because on those little scales, matter, dark matter plus normal matter combined, can win. But between those clumps of matter, between the galaxies and the groups and the clusters of galaxies, dark energy wins. Dark energy says, see ya, you're going to see each other never, bye bye, out of reach, expanding away. So dark energy is like this relentless push outward that just says, oh, I'm empty space, and I'm going to make more empty space, and I'm going to push you further that way and you further that way, and everyone's going to get farther apart. And dark matter's like, oh, but there's so much of me over here and over there, and maybe we can get together before the dark energy wins, but all the stuff way over there, I'll never get that. Nope, dark energy is too relentless. So that's a difference between dark matter and dark energy. Dark matter tries to hold it together, and on the small scales it can, but on the large scales, only dark energy matters, and everything gets driven apart.
Wow.
I have so much more. Oh my gosh.
Dark energy is your reality check, friend. Dark matter wants you to go out and get wasted.
I like.
You think we have time for a couple more questions from our live chat, or?
Yep. Yep. That's what I was gonna absolutely pull up
If Ethan
if I
has
can.
time for it.
Yep. One is from Puck. What's easier, learning the science first than learning to be a good science educator, or being a good educator first and learning the science later?
You know, you hit on the important part, is that you have to know both. You have to know both. You have to be good at educating, because that is an art form. And you also have to know what you're talking about, because you can be the greatest teacher in the world, but if you don't have anything of value to teach, why would anyone listen to you? So I think you have to do both. For me, personally, I think it's easier to teach scientists how to communicate than it is to teach communicators how to science. But that's just possibly my own bias, because one of the things that inspired me, unlikely story, I know, one of the things that inspired me that I could do science communication was when I watched the movie Miracle, which was a retelling of the 1980 so-called Miracle on Ice, where the United States amateur men's hockey team defeated the Soviet Union in the gold medal game at the Olympics in 1980. And this was called the Miracle on Ice. Because the Soviet Union had the Soviet Union's best pro hockey players, and the United States beat the Soviet Union and then beat Canada and won gold, and it was crazy. It was pandemonium. They remade the movie. They made a movie about the event 20 years later, and they said when they were casting the movie, what are we going to do? Are we going to get like the young, successful actors with the big names to play the hockey players and get people to the movie, and then we're going to teach them how to play convincing hockey? Or are we going to get some Canadians who've been skating since they were 2 years old, who've been playing hockey for their whole lives, and cast them and teach them how to act? And I think about science communication like I think about that. If you've been doing science your whole life, and you've done it at a very high level, and you have that expert knowledge, that's not something you can fake. That's a lot of information to acquire. And I still like to think that having knowledge and information means something. It means something more than, oh, well, I like the sound of my own voice, and I can go on the internet and I can put some things. Yeah, but if you don't know it for yourself, it's not you who's putting it together. And I think you need to have that quality, sound, professional judgment in order to be able to separate fact from fiction, in order to be able to say, no, look at these important points. This, those are the three things you need to keep your eye on to know whether this claim is true or not. So I think there's room for both, right? Bill Nye is not a scientist, great science communicator. But if you said, Ethan, I want Bill Nye to write this Encyclopedia Cosmologica, I would tell you, no, you probably don't. You
Right.
probably don't. So I think both are important, but I think that you have to have the knowledge. You have to have, I know this thing of value to be able to communicate to others. So in a sense, although I do think communication takes its own skill set, I will say people with a skill for communication and a talent for science will do better at communication than people with who work hard to become skilled at science but are talented at communication. I think the science is the harder part than the communication. But I think that because, that's where my background is. And if I was the other way around, I would think the other way.
I want to thank Dr. Tapioca Weasel, who gave $5 in a super chat. I have actually two blocks of questions. He asked actually 6 questions. And
Oof.
Dr. Tapioca
Rapid
Weasel,
fire. Come on, I love
I can do
tapioca.
that. Okay, I can do that. Before I go to him, and whatever we don't get to, I will keep, and we can
just
have
get a
you on
couple of
again.
super stickers too. So
here's the first one from Logan Fisher. It doesn't show up here, but he gave a cute little animal, like shaking his little pom-poms. Yeah, it's really cute. And then the next one, again from Logan Fisher, who gave us $2.99 the first time, $4.99 the second time. Thank you. This one has a little dude dancing. I wish it would show up on the screen like that because it's pretty cool.
Well, there's a little woman head, dude. Yeah.
All right, so we will go to Dr. Tapioca Weasel and we will try to get in what we can. So the first one is, what percentage of heavier than iron nuclei are from colliding neutron stars versus supernovae? I don't know if I said that right. Supernovae.
That first one, you do make heavy elements both in supernovae. You make some from dying red giant stars, and you also make them from colliding neutron stars. It turns out that the line between where are your elements made mostly from supernovae versus where are your elements made mostly from colliding neutron stars is element number 40, zirconium. Below element 40, you're likely to be made from a supernova. Above element 40, you're likely to be made from colliding neutron stars or a kilonova. And that is the answer to your question number 2. What is a kilonova? It is when 2 neutron stars collide and boom, they may either make another neutron star, they may go direct to black hole, or they may do what we observed GW 170817 did, which is they will briefly make a rapidly spinning neutron star that then in less than a second collapses to form a black hole. But it's the ejecta, which we think only happen when you have a neutron star collision. It is the ejecta from that make those heavy elements above zirconium and also that emit a wide source of gamma rays. We believe this is one of the origins of gamma ray bursts.
Awesome. So is the universe infinite?
The answer is the part we can see is not. The part we can see is finite, right? The part of the universe we can see is finite. It goes out now 46.1 billion light years because that is the amount of distance that a photon that was emitted at the Big Bang would have traveled to reach our eyes today. There is almost certainly light beyond that is on its way, that just hasn't gotten here yet. That as the universe keeps expanding, some of it will get here and some of it is too far away to ever get here. But we don't know whether it's infinite or not. We only know lower limits.
I'm so sorry, Bre. She's like trying to peek up over the thing, but I'm going to do it again. So we're going in rapid fire. So I can't say that. Are you familiar with Pierre Marie Robitaille's? Woo! Bonkers criticism of the CMB spectrum.
For once, thank goodness, no, I am not aware of his criticism of the CMB spectrum, but I will say that the CMB spectrum was measured so precisely by COBE, the Cosmic Background Explorer satellite from the 1990s, that John Mather won a Nobel Prize for his work on, that is the most perfect black body spectrum we've ever observed. So if someone wants to argue it's of non-cosmic origin, I will point you to the COBE work and show you that at most 1 part in, I believe it's 3/100,000ths of the CMB could be of non-Big Bang thermal origin. No more than that. So no, I'm not familiar with Pierre-Marie Robitaille's bonkers criticisms of the CMB spectrum, but it is the most perfect black body we know of in all of existence. So if someone has criticisms of it, they better bring the big gun, because we have the big data.
Okay. Where did that one go? Hold up a second. Where did I? Okay, here we go. I don't know what just happened there. Gravitational wave measurements from pulsar timing, are they reliable?
They are reliable. In fact, I have a podcast coming out on this on Saturday. I got to talk with postdoctoral fellow, Einstein postdoctoral fellow, Dr. Thankful Cromarty at Cornell, who was one of the leads on the nanograv collaboration, which just announced the first, they can't say detection, but the first evidence for the gravitational wave background of the universe, which looks like it's due to orbiting supermassive black holes. Now, are the measurements from the pulsar timing reliable? They're reliable enough that we can say there's a signal there that they're seeing. They're not yet reliable enough that we can say, oh, and it's definitely primarily from orbiting supermassive black holes. So
And
we have detected it, we've seen it, but we haven't yet characterized it.
all right. And finally, he wants you to steelman geocentrism.
Sure. This is a fun little exercise. You know, you could say a lot of things, go around a lot of things from a lot of perspectives, but I've never seen a Foucault pendulum without a magnetic kicker really do its Foucault thing. So I don't really know. Maybe it's not the Earth that's rotating. Maybe every day, every 24 hours, the whole universe rotates around me, and it's not subject to the speed of light limit that everything else in the universe is, because I say geocentrism is the best centrism. I don't know
love
how
it. That was
steelman
awesome.
that was, but how did I do?
That was yeah.
I love it. I love it.
You had science in there. There was
Yeah.
science stuff mentioned.
Look, got my
Pendulums
hair
and
all
such.
screwed up now. Okay. Well, now
Thank you, Dr. Tapioca Weasel, for your hilarious and awesome and informed questions as well. Yeah, that
Oh,
last
loved
one
I
it.
was
feel
easy.
like that was pretty good. That was like someone stuck the key in my back and said, go,
Yeah.
go, go.
Yeah.
You cannot say now that I am full of questions. We can now say that it's only Dr. Tapioca Weasel. He is
And Dr.
beat me.
Tapioca Weasel is a physicist. So yeah.
Oh,
They know
I
their
didn't
business.
realize I was getting questions from someone who knew the answers. Well,
Yeah.
I hope he doesn't sick his Tycho Brahe's ghost on me.
we may have to have you both on. Wouldn't that be cool?
You know,
Oh, yeah.
I've been game for weirder things than that.
Well, I want to thank you so much for coming on.
You know, thank you for having me and giving me a chance to answer all these fun questions, to hang out with all you beautiful geniuses, and also to get a chance to talk about some of the projects I've been working on. Encyclopedia Cosmologica, The Littlest Girl Goes Inside an Atom, is now available on Amazon, so you can order it anywhere in the universe. And if you order the Encyclopedia Cosmologica today, you will have it in time for the December holidays, Christmas, Hanukkah, Flying Spaghetti Monster, Feast of Festivus, whatever your holidays are.
Yay, awesome. For all of you, if you like this content and you want to see more of it, like, subscribe, hit the bell, share, all those good things. If you really want to help us, consider becoming a patron Patreon, if I can say it right. So we want to thank Sydney Davis Jr., Erica Zoles, Tara S., Ryan, Deneen Murphy, Dan D., Michael Wiseman, Kathy Cotton, Cindy Plaza, me, Aaron Colson, Phil Calderon, and Jamie West. And now,
Yeah,
I'll
don't
leave
forget to
this for
check
you.
out the other shows on Skeptic Haven. We got Secular Soapbox on Wednesday. On Thursday, you got me and Sunny here on the Sunny Spot, back to our regularly scheduled programming. We've got Saturday with the Global Atheist and Women Atheist Unloaded. And on Sunday, we got Let's Talk. So, yeah, thank you so much. You silly girl.
Well, I get it from you because we're a good team. So, in the meantime, always remember to think critically, everyone. Have a great evening. Bye.